All right, let's jump right in and talk about a fascinating little component that solves a really big electrical puzzle. So here's the big question, the one that kind of seems to break the laws of physics. If you give a motor 120 volts, how in the world can it turn around and generate an even higher voltage inside itself? I mean, it sounds impossible, right? But it's the absolute key to how these powerful high torque motors get the job done. Well, the secret isn't magic. It's actually a super clever piece of engineering, and it all revolves around this one smart switch, the potential relay. You could say it's the brains behind the brawn. Okay, so to really understand how this all works, we first need to meet the key players inside the motor. Think of it like a team, where everyone has a very specific job to do. First up is the run winding. This is the workhorse, the marathon runner of the motor. It's designed to be super efficient and just run and run for long periods. But like a marathon runner, it's not the best at getting a quick start from a dead stop. And that's exactly where the start winding comes in. This is the sprinter on the team. It's built for one thing, a short, incredibly powerful burst of energy to get that motor spinning. But just like a sprinter, it can't keep that pace up for very long. So, to give our sprinter that explosive start out of the blocks, we have the start capacitor. It's like a battery that stores up a bunch of energy and then releases it all at once in a powerful kick, giving the start winding the juice it needs to create that initial turning force, what we call torque. And finally, we have the coach of the team, the potential relay. It's a voltage-sensitive switch, and its whole job is to watch the motor's performance and make that critical call to pull the sprinter, our start winding and capacitor, off the track at exactly the right time. So we've met our team, but how do they all work together to create that extra voltage? Well, the secret is you have to stop thinking about this as just a motor. This quote from our source material really nails it. For just a split second during startup, the parts of the motor stop acting like a motor and start acting like a step-up transformer. And here's how that analogy works. It's a pretty cool one-to-one comparison. The run winding acts like the transformer's primary coil. The spinning rotor in the middle, that's our iron core. And here's the kicker. The start winding, with all its extra turns of fine wire, acts as the secondary coil. And if you know anything about transformers, you know that's the key to stepping up voltage. So, how does this little temporary transformer actually build up a higher voltage? Well, it all comes down to a really cool principle called magnetic induction. Okay, here's the play-by-play. The run winding creates a magnetic field, and that gets the rotor spinning. Now, as that rotor gets up to speed, its own magnetic field starts expanding and flashing or sweeping across the wires of the start winding. And because that start winding has way more turns of wire, this interaction doesn't just create a voltage, it amplifies it, stepping it way, way up. And the result is honestly pretty amazing. A motor that's just running on a standard 120-volt circuit can suddenly have over 180 volts pulsing through its start winding. It's literally creating its own extra power right on the spot. Now, this isn't some random electrical glitch. This phenomenon has a name. It's called back electromotive force, or back EMF. It gets the name back EMF because it's a voltage that actually pushes back against the original current. It's a totally predictable and, more importantly, usable force that the motor generates all by itself. And that brings us right back to our smart switch. Because that back EMF, that extra voltage, that is the exact signal the potential relay has been listening for. Now, this is maybe the most important thing to get about how this relay works. Its contacts start out in a normally closed position. So what does that mean? It means the circuit is already complete. The moment you flip the switch, power flows to both the run winding and the start winding at the exact same time. There's no delay. It's what gives the motor that instant, powerful kick. So the relay's internal coil is basically just a sensor, and it's constantly reading that rising back EMF. As the motor gets close to about 3/4 of its full speed, the back EMF finally hits a critical number, a specific level we call the pickup voltage. And that voltage is just high enough to create a magnetic field inside the relay that's strong enough to physically pull that switch open. And click. The connection is broken. The sprinter and that power boost capacitor are now safely disconnected from the circuit. Their job is done. And that right there is the beauty of this whole system. It's a design that perfectly and automatically balances raw power with self-protection. It's really elegant. So let's just sum it up with this chart. You've really got two states. When the motor is starting, the relay is closed, keeping all those starting components in the circuit for maximum torque. Then, once it's up to speed, that back EMF pulls the relay open, taking those components out of the circuit so they don't get fried. So why does all this matter? Well, it's the best of both worlds. You get that huge burst of power you need to get something heavy, like an AC compressor, moving from a standstill, but you also protect the delicate wires of the start winding from burning out. And once it's going, the motor can just cruise efficiently on that beefy run winding alone. It kind of leaves you with this final thought, right? For that one brief, critical moment of startup, the answer is pretty much yes. It's a motor that cleverly transforms itself to generate the very power it needs to get going. A pretty cool hidden secret. Now explained.